Today, we are discussing current mirror circuit using MOS transistors. Current mirrors are fundamental circuits in analog design, building upon the concepts of current sinks and sources. By leveraging the property that MOS transistors with equal gate source potentials have equal channel currents, these circuits find applications in biasing and amplification. Let's explore their design and operation in detail. Here's a simple schematic of an N-channel current mirror. The input current, II, sets the operation, while the output current, IO, mirrors it. M1 operates in the saturation region, ensuring stable operation. The current ratio is determined by the device parameters and their aspect ratios, which are under the designer's control. This relation is depicted in equation 1 using the MOS transistor drain current equations. For ideal current mirrors, we assume both transistors are on the same chip, sharing identical parameters such as threshold voltage and transconductance. When the drain source voltages are equal, the current ratio becomes directly proportional to the aspect ratios, providing a predictable and designer-controlled behavior as width W and length L are under control of the designer. This relation is depicted in equation 2 and equation 3 respectively. Real-world current mirrors face non-idealities. First, channel length modulation causes deviations in the current ratio due to varying drain source voltages. Second, threshold voltage offset, though typically minimal in modern processes, can lead to errors. Lastly, geometrical mismatches during manufacturing can also impact performance. Channel length modulation occurs when drain source voltages differ, causing deviations in current mirroring. This equation shows that differences in drain source voltages of the two transistors can cause a deviation from the ideal unity current gain or current mirroring. A plot of the current ratio error versus the drain source voltage difference, VDS1 VDS2, for various values of lambda, channel length modulation parameter, is shown considering both transistors operating in the saturation region. Two key observations emerge from this plot. Significant current ratio errors occur when the drain source voltages of the mirror transistors are not equal. For a given difference in drain source voltages, the accuracy of the mirrored current ratio improves as lambda decreases, indicating higher output resistance. Therefore, an effective current mirror or amplifier design requires matching drain source voltages and maximizing output resistance. The second non-ideal effect is the threshold voltage offset between the two transistors. In clean silicon gate CMOS processes, this offset is typically less than 10 MV when the transistors are identical and placed in close proximity. For a pair of transistors configured as a current mirror, where the drain source voltages are equal and all other parameters are identical except the threshold voltage, the behavior simplifies as described by equation -1 as depicted by equation 4. Plot illustrates the ratio error versus the threshold voltage difference, delta VT. The graph clearly indicates that the performance of the current mirror improves at higher currents. This is because a higher current results in a larger gate source voltage, VGS, making delta VT a smaller percentage of VGS, thereby reducing its impact on the current ratio error. The transconductance gain, K, of the current mirror may also exhibit mismatches, often caused by oxide thickness gradients. To analyze the impact of variations in both K and the threshold voltage, VT, consider a scenario where the W by L ratios of the two mirror transistors are identical, but KKK and VT are mismatched. Under these conditions, equation -5 can be reformulated to account for these variations. The third significant non-ideal effect in current mirrors arises from errors in the aspect ratios of the transistors. These errors are due to physical variations in width, W, and length, L, stemming from processes like photolithography, etching, and outdiffusion. Such variations can occur even for transistors placed side by side on the chip. Geometrical mismatches directly impact the accuracy of current mirrors. Any deviation in W by L ratios leads to inconsistencies in the current ratios, compromising the circuit's reliability. Minimizing these mismatches is crucial for precision design. To minimize the impact of geometrical mismatches, designers can increase the transistor dimensions significantly beyond the expected variation range. For instance, using W and L greater than 10 micrometer typically ensures that geometrical errors become insignificant compared to other non-ideal effects like offset voltage and channel length modulation. In designing robust current mirrors, choosing larger transistor dimensions and employing precise manufacturing techniques are key strategies. Additionally, placing transistors close together and using advanced layout methods like common centroid designs can further mitigate mismatches. In certain applications, current mirrors are designed to multiply currents, functioning as current amplifiers. This is accomplished by making the aspect ratio of the multiplier transistor, M2, significantly larger than that of the reference transistor, M1. To achieve optimal performance, the geometrical aspects of the design must be carefully considered. The small signal output resistance serves as a critical indicator of how well a current mirror or amplifier performs. For the basic N-channel current mirror shown in figure -1, the output resistance is defined by equation -7. A higher output resistance translates to improved performance and accuracy of the current mirror. To achieve superior performance, advanced current mirror designs prioritize increasing the output resistance. A higher route enhances the circuit's ability to maintain accurate current mirroring even under varying load conditions. This improvement is crucial for minimizing errors arising from inherent non-idealities. Would see the improved current mirrors in Part 2.